Activation functions are mathematical equations that determine the output of a neural network. They transform the input signal into an output signal, introducing non-linearity into the network's learning process. In simpler words, these functions decide whether a neuron should be activated or not, based on the relevance of its input. Let's explore why we need activation functions. Without activation functions, neural networks would simply be linear regression models, regardless of how many layers they have. Each layer would perform a linear transformation of its inputs. This means the network cannot learn complex patterns or solve nonlinear problems like image recognition or natural language processing. The code snippet demonstrates that multiple linear layers combined together results in just another linear function, which is not what we want for complex problem solving. Here we compare linear and nonlinear activation functions. A linear activation function results in an output that is directly proportional to the input, therefore it cannot learn complex patterns. It does not provide solution for problems like the XOR problem. On the other hand, a nonlinear activation can approximate any function. It handles complex relationships and enables deep learning. Let's discuss some common activation functions. First is the sigmoid function, denoted as sigma of x, which equals 1 divided by 1 plus e to the power of negative x. It has an output range between 0 and 1, and produces a smooth gradient. However, it suffers from the vanishing gradient problem and is not zero-centered. Next is the hyperbolic tangent, also known as tan of x, which equals e to the power x minus e to the power of negative x, divided by e to the power x plus e to the power of negative x. Its output ranges from -1 to 1, it is zero-centered and has stronger gradients but still has the vanishing gradient problem. Now let's talk about the next important activation function, that is ReLU, also known as rectified linear unit. It is defined as f of x equals the maximum of 0 and x. This activation function does not have the vanishing gradient problem and is computationally efficient, with sparse activation. A problem with ReLU is the dying ReLU problem. Next is leaky ReLU. It is defined as f of x equals the maximum of alpha times x and x, where alpha is approximately equal to 0.01. Leaky ReLU prevents the dying ReLU problem, allows negative gradients, and facilitates better backpropagation. However, the results can be inconsistent. Choosing the right activation function depends on the specific task. For hidden layers, ReLU is commonly used because of its fast training, ability to solve vanishing gradients, and sparse activation. For binary classification tasks, Sigmoid is recommended since the output is between 0 and 1, which is ideal for binary decisions. For multi-class classification, softmax is preferred as it normalizes outputs into a probability distribution. Finally, for regression tasks, a linear activation or no activation is typically used, providing an unbounded output range for prediction tasks. Activation functions have a huge impact on training dynamics. ReLU networks generally train faster due to consistent gradient flow, whereas sigmoid or tan networks may slow down as gradients become smaller. Non-saturating activations like ReLU maintain stronger gradients throughout training, leading to more stable learning. Also, activation functions can lead to varied feature representations. For example, ReLU promotes sparsity, while sigmoid and tan create dense representations. Simple functions like ReLU require fewer computational resources, which enable faster forward and backward passes during training. It is important to use appropriate weight initialization based on your activation function. For ReLU, He initialization should be used. Also, consider using different activation functions in different layers based on their specific requirements and characteristics. Another best practice is to track the distribution of activations during training to detect potential issues like dying ReLUs or saturation. A common issue is dying ReLU, where neurons become permanently inactive, which can be solved by using leaky ReLU or adjusting the learning rate. Another problem is vanishing gradients, where gradients become too small in deep networks. for which ReLU variants or skip connections can be used. Lastly, exploding gradients is another problem where gradients become too large during training, which can be solved by using gradient clipping and proper initialization. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.